Hi, my name is Daniel Odamelum, and this is Project 3.3.4, CHUMP, the RAM, MUX, address, accumulator, and control EEPROM. This part of CHUMP finally integrates all the necessary chips to complete CHUMP's data path, resulting in the fully functioning 4-bit computer. Here you can see my code running, which simply adds and subtracts, storing some values to RAM along the way, and checking if it's 0. The main purpose of this program is to demonstrate how the if 0 flag is used in CHUMP for branching instructions. The 74LS189 RAM is a 64-bit memory device that CHUMP uses to store variables, user inputs, and intermediate results during program execution. It contains 16 memory addresses with space for 4-bit nibble in each one. Its 4 bidirectional data pins, D0 to D3, are used for reading and writing data, and 4 address pins, A0 to A3, decide which of the 16 locations of memory the RAM reads to or writes from. Its data outputs are inverted, which means you have to use an external inverter gate flip-flop, which is the address register, its proper outputs. Stores the 4-bit address. The data pins enter a high impedance state needed by CHUMP, which means RAM disconnects from the data bus and receives values, which are used prevents conflicts when the accumulator sends data to RAM. On the clock's rising edge of the signal, the register 189 relies on 2 active load pins on the data bus and holds it on its outputs. Write enable. As such, to determine whether it continuously drives the RAM's address occurs when CS is 0, and every instruction other than those that require RAM to write to send data as a bus function, while writing the address pins are 0, causing RAM to store whatever value is currently placed on the bus. While CS is held low, so the chip is always enabled, the control EEPROM toggles the WE pin by sending control signals based on the opcode received by the program EEPROM. The 74LS157 quad 2-to-1 multiplexer, MUX, determines which data input, A or B, is sent to the ALU, program counter, and address register. Each channel receives a value coming from RAM or constant from the program EEPROM. That would be B and A inputs respectively. The MUX then selects between these two inputs via the active low select pin, and when it's low, the MUX outputs the value on its A inputs, the constant, and when it's high, it outputs the value on its B inputs, the 4-bit output from RAM. Because the low bit of the opcode, OP4, determines whether the RAM is being accessed or not, the S pin is tied directly to that output from the program EEPROM, which gives us one of the control codes. Therefore, the MUX decides whether the ALU uses an immediate operand from the program EEPROM or a stored memory value from RAM when computing an instruction. The 74LS174 HexD flip-flop, which is the address register, stores the 4-bit address pointing to the current RAM location needed by CHUMP. It has 6 D flip-flops, 4 of which are used for CHUMP's addressing. On the clock's rising edge of the signal, the register latches whatever 4-bit value is present on the data bus and holds it on its outputs. As such, the address register continuously drives the RAM's address lines. In other words, every instruction, other than those that require RAM to write, can be considered as a read function, updating the address pins of RAM. The 74LS377 octal D flip-flop, the accumulator, is the main register of CHUMP and stores the results of all operations performed by the ALU. This octal D flip-flop latches the ALU's outputs on the next clock tick when the chip enable pin is low. This causes the accumulator to basically mirror the ALU's outputs unless an instruction like store to or read or a branching function is called. Its output is also fed directly back into the ALU's A input, making it important for arithmetic comparisons and the conditional branching instructions. The AT28C16 control EEPROM coordinates the entire CHUMP architecture by generating the control signals that govern when each component reads, writes, latches, or drives the data bus. The 4 opcode bits from the program EEPROM act as the address inputs to the control EEPROM, so each instruction corresponds to a unique 8-bit control code. The 8 output lines of the control EEPROM serve as the following control codes: RAM's write enable, the accumulator's chip select, and select 0 to 3 mode and carry in for the ALU. The other 2 control codes are taken care of in hardware as based on the table shown. The select input of the multiplexer is always the same as the low bit of the opcode, and ANDing the high 2 bits of the opcode will provide the necessary logic for determining if the instruction is branching or not. Here, you can see a simple code created by Feinberg that adds 1 and stores it in the accumulator repeatedly, meaning that every time the code runs through, this value in the accumulator increases by 1. My name is Daniel Odamelum, and thank you for listening.